Okay, we will now talk about antigen presentation. So the basic idea is lymphocytes need to be presented with the foreign antigen. All right, and there's two ways this is done based on who you're presenting the antigen to. So this one here is showing what we call an antigen presenting cell. So this is a cell right here that one of its major jobs is to go around looking for an antigen, all right, endocytosing it, okay, so these cells are typically going to be your phagocytes. So for example, macrophages are APCs or antigen presenting cells, and dendritic cells are antigen presenting cells. So this could be, let's call this maybe a virus that hasn't infected a cell yet, or maybe it's a bacterium that's kind of loose and causing infection. This APC phagocytoses, brings it in, digests the bacteria or virus into pieces, all right, using the enzymes of a lysosome. Then it uses what's known as the MHC2 receptor, all right? And what that does is it grabs a little piece of the antigen and sticks it on the outside of the cell. So what that's doing is showing a lymphocyte. Now the question is, well, what lymphocyte? The answer is a helper T cell. So APCs, antigen presenting cells, present the antigen to the helper T cells. So it's basically a way to notify the helper T cells that, listen, you got to start helping out around here because we got this antigen and we need help. All right. So that's how APCs present to helpers. Other cells that can do it are when they're infected. All right, so this now is not a macrophage, it's not an APC. It's a cell that got infected. All right, so now this purple thing is what we call endogenous. That means it's inside of the cell. So remember, the previous one was outside the cell, but it got phagocytosed. This is a bad deal here. This is an infectious virus or intracellular pathogen. All right. Same process happens. It gets kind of chopped up into fragments. It gets presented. Now, it's a different MHC receptor. This MHC receptor is called class 1. And we're going to talk about why you need two different ones coming up. But if you're an infected body cell, you're going to use MHC1 to present the antigen on the outside, but because you're using an MHC1, it's not a helper that comes over and sees this. It's a cytotoxic T cell. So when a cytotoxic T cell comes over here and sees this, it's going to destroy this infected cell. All right, because remember, this could be a virus that's replicating inside of the cell. All right, so it's kind of the same big picture presenting the antigen, but it's a different cell in each situation, and it's a different MHC, and it's a different lymphocyte that's being presented to. All right, okay, so we're going to kind of start the process from the beginning and look at a helper, then a cytotoxic, then a B cell. So notice what we have here. We have an APC. It phagocytosed a pathogen. It processed that pathogen. It digested it into pieces, and it's presenting. So here's that antigen presentation. So if we expand on this, and this kind of panel, we've got the MHC2 presenting the antigen. The helper uses what's called the TCR. That's the antigen receptor. In this case, they're calling it a T cell receptor. But that's the antigen receptor. Notice it attaches to the antigen. Then notice you have a CD4 protein or receptor that attaches to the MHC2. So this is a form of communication, basically. It's using two receptors, right, TCR and CD4, on the helper to identify that we've got presentation going on. All right? So what's this going to lead to? So let's kind of start from the beginning. An APC phagocytoses the pathogen. It presents it using MHC2. Again, that's the green thing. The helper T cell uses its T cell receptor, aka antigen receptor, to attach or bind to the antigen. And it uses its CD4 receptor to bind to and attach to the MHC2. So think about what this means. It's kind of like having two locks and two keys, and you turn the two keys and now you get activated. So this is telling the helper, number one, that there's an antigen loose. All right. Number two, it knows that this must be an APC because it's got this MHC2 here. All right. And once that happens, once these interactions occur, that's what causes the proliferation and activation of the helper T cells. All right. So now instead of having one, you're going to have multiple, hundreds, maybe thousands of these helper T cells that all got activated. What does it mean to be an active helper? It means you're going to secrete what's known as interleukin 2 or IL-2. And that is an immune system booster. All right? That's a key ingredient to have a nice, strong immune response. All right? Which we often just refer to as helping. At the same time, you're also going to produce memory helper T cells. All right? And those cells are going to wait, right? They're going to say, you know what? I'm going to hold off, but now I'm going to have many more cells available if we ever get exposed to the same antigen. All right? So let's look at how a cytotoxic T cell works. Same idea, it gets presented an antigen, but in this case, it's from an infected body cell. All right? So you have an infection. Let's say it's a virus. That virus gets into the cell, so now we've got an infected cell. That's going to have to present. So this infected cell uses MHC1 to present the antigen, but because it's MHC1, it's not a helper, it's a cytotoxic T cell, because a cytotoxic T cell uses its TCR to recognize that there's an antigen, but its CD8 receptor locks in with the MHC1. All right? If that happens, you also need co-stimulation. So notice we got a helper over here. Got to have that helper. All right? If you don't have a helper, this isn't going to occur. The helper co-stimulates with interleukin 2. You get proliferation, activation of many clones, and you get destruction of that infected cell. All right, so this cell here kills this cell here. And this cell might then release the virus, but now we can attack the virus with an antibody. All right, so this is the process by which cytotoxic T cells get activated. And then the same is true, you're going to produce some memory cytotoxic T cells. How do cytotoxic T cells kill the infected cell? They use molecules. Some examples are called granzymes, granulysin, and perforin. We're not going to go crazy here, but you should recognize, if you're ever asked, that these are molecules released by the activated cytotoxic T cell to kill the infected cell. This is basically showing the same thing, but over here, this cell happens to use what's called granzymes. This cytotoxic T cell happens to be using granulysin and perforin. Ultimately, we kill the infected cell, and if the virus or microbe gets released, we can phagocytose it, we can use antibodies, but at least we don't have an infected cell with a virus replicating inside of it. So my analogy here is if we have a country that's harboring an enemy, right? Let's say there's a country that's letting an enemy of the United States train in their country. Well, we kind of think of them as just as guilty as the enemy, right? Because why are you letting this enemy train basically against the United States? So we often have sanctions against that country, all right? And we try to do things to prevent this. In this case, we kill it. We kill the cell, all right? And we hope we can replace that cell. So if this was, let's say, influenza, once we kill this infected cell, we can just replace it. We can have another cell, divide and replace it. In some cases, we might not be able to replace the cell. So that happens with polio. So polio is a virus that infects a neuron. Well, we don't have the ability to replace a neuron that has been killed. All right, so that's why polio leads to paralysis, because we just can't reform the neurons that the virus has killed. But luckily, we have a vaccine that will prevent polio. All right, so now let's switch gears and look at B cells. Kind of similar, right? You're going to have some sort of B cell receptor on the surface. That's going to recognize a microbe. All right, so here's a microbe. Let's say it's a bacterium. And this is a B cell that has a receptor that recognizes this little antigen on the microbe. We need that helper. So again, you kind of always need this helper that's co-stimulating here. And then you're going to get proliferation. So these B cells are going to clone themselves and replicate and become plasma B cells. Plasma B cells are going to secrete antibodies into your body fluids. All right. And these antibodies are then going to go look for the antigen. And we'll talk about how they help get rid of the antigen in a little bit. We're also going to produce longer-lived memory B cells. So now you're going to have these guys ready to go upon second exposure. Let's kind of think about this second exposure. So this is a graph. Every book's got a similar graph that explains this idea of memory in the context of B cells. So this x-axis is days, right? So on day 0, they say you were exposed. Okay, what could that exposure be? Well, maybe you picked up the influenza virus, right? Someone sneezed, you breathed in the virus. All right, that could be a first exposure. The other option here is it could be a vaccine. So you might have a first exposure by vaccination. All right, what happens? Well, activation, proliferation, all of a sudden you get a production of antibodies. Now, this shows two different types of antibodies, which we'll talk more about a little bit later on. But the first type of antibodies that get produced are known as IgM antibodies. And Ig stands for immunoglobulins. So it's a type of, or it's a class of antibodies. But they're known for being kind of the first ones to be produced. Then your B cells switch. So notice that the IgG antibodies get produced a little bit later. If this was a true kind of graph, it might be, 5 or 6 days later, all of a sudden you get IgG antibodies. Now you hope by then, right, you're a couple weeks into the illness, maybe you're starting to feel better, right? So if this was the flu, hopefully this amount of antibody is enough to make you start to feel better, 2 weeks later. Now, if this first exposure was a vaccine, you wouldn't be sick, right? So the difference between an exposure to the pathogen versus exposure to a virus is you're sick as a dog for these 14 days. Whereas if it was the flu shot, you're not sick, all right? But in both situations, you're generating memory. You're generating memory B cells. So now maybe a couple weeks later, you get exposed again. Maybe, someone sneezes on you and it's the exact same virus. So it has to be the exact same virus. Since you have memory B cells, you're going to get a huge, quick production of IgGs. Notice this happens maybe a day or two after exposure, whereas here it took a while to get some antibodies being produced. And this overproduction of IgG antibodies is why you might not even know you were exposed, because these antibodies prevented the virus from getting into cells. All right? So this is a graphical representation of immunological memory. All right? All right, so let's talk about antibodies. Antibodies come in different classes. All right, and they all start with this Ig. So Ig stands for immunoglobulins. All right, and I can't believe I don't have that word on here anywhere, but you could always Google it. But immunoglobulin. It's basically another name for an antibody. I want you to know the different classes. This is a lot of information here, so I tried to simplify it over here. So IgMs, what do you need to know? Well, first and foremost, they look a lot different. They're what we call a pentamer. Penta means 5. So they've got 5 of these units right here. All right, so they're big antibodies. They're the first class to be released. We saw that on the previous graph. All right, then we're going to switch over to IgGs. They're also the antibodies that are the anti-A and anti-B antibodies in blood typing or blood compatibility. And that should make sense because these things are so big, they can't cross the placenta. So you can actually have a mother who's type A and a fetus who's type B, and the mother's antibodies won't attack the baby's blood because these antibodies are too big. Now, if it's an Rh issue, Rh antibodies are small and they can actually cross the placenta. So that's why you got to be very concerned when a mother is Rh negative and a baby is Rh positive. All right. IgA antibodies are dimers. So notice it's got 2 of these units here. And an antibody unit kind of looks like the letter Y, where these ends here and here is what recognizes or attaches to antigens. So those are called the antigen binding sites. So you'll notice that this guy has 10 antigen binding sites. So it can attach to 10 antigens. This guy has 4. It's got 1 there, 1 there, 1 there, and 1 there. But IgA antibodies are best known for being in certain body secretions. All right, these secretions include saliva, sweat, intestinal secretions, the antibodies that are found in breast milk that can be passed on to babies are IgA antibodies. All right. IgD antibodies are the B cell receptor. You should have noticed that on the surface of that B cell, the receptors kind of looked like antibodies. They looked like that kind of letter Y. So IgDs are just basically another name for the B cell receptor. IgGs are the most abundant. So they're the ones, when you're sick, they're working for you. All right, so they account for 75 to 85% of the antibodies that are circulating around in your body fluids, fighting against bacteria, viruses, toxins that might be in your body. These are the guys. All right, these can also be given to other people. So passive immunity, we'll talk more about that, is that when we harvest antibodies from one person's blood and we can give them to someone else to help them fight the infection. That was done for COVID. It's done for a lot of it's done for Ebola and other situations. Then the last class is IgE antibodies. These guys are involved in allergic reactions. So they're found they cause basophils and mast cells to release histamine. So if you have an allergy or someone else you know has an allergy, the allergen gets bound to the IgEs, and then this triggers histamine release. And histamine is what causes all those bad signs and symptoms of an allergic reaction, which is, severe inflammation. You might get constriction of the airways, and that's largely due to the involvement of IgE antibodies and the basophils and mast cells. Okay, that's going to be a good place to stop, and then we're going to start and kind of finish the chapter in the next video. So the next video is going to be just kind of wrapping things up.